In this video, we're going to solve trig equations. There are two parts to this video. In this first part, I'm going to introduce finding solutions to trig equations, even though those trig functions are periodic and have infinitely many solutions. We'll also be working with our inverse functions and the restrictions on their ranges. Let's go ahead and start off with this first example. We've got example 1, sine of x is equal to 1/2. I have the graph of sine here. So this is sine of x, and this is x. And I can go ahead and locate where the output is equal to 1/2. It's going to be a height here. So I know that I've got solutions, these x values, wherever I'm lining up with a height of 1/2. And because this is periodic, it goes on forever and ever and ever. Well, the first question, though, is how many solutions per period? One period is 0 to 2 pi. So on 0 to 2 pi, I have two solutions, one there and one there. So there are two solutions per period. I'm going to call these our base solutions, and that's really helpful for finding a form for the infinitely many solution set. How many solutions total? Okay, I just said it. Infinitely many. For this one, we want to find the solutions on that interval 0 to 2 pi. Well, I want the sine of x. I want the angle whose sine is 1/2. It's a 30, 60, 90 triangle. 1/2 is going to be here, so I want the smaller angle, pi 6. On my unit circle, it's this one here, which is pi 6. And the other one in quadrant 2, which is going to be, so I've got pi 6 and pi minus pi 6. These are always supplementary, which makes it nice. So that's going to be 5 pi 6. So 5 pi 6. I did not use a sine inverse. We will see some examples of that, but keep in mind that sine inverse is only going to give you a value between negative pi halves, negative 90 degrees, and positive pi halves. It will only give you the acute or the smaller angle, not the obtuse angle, which is larger than 90 degrees. Okay, so our two solutions are pi 6 and 5 pi 6. From these two solutions, which I call our base solutions, they're the first two that we come up to in our first positive period, we want to express the general solution. Well, I'm going to come up with solutions every time I travel 2 pi. So plus 2 pi, plus 2 pi, and then it will happen again and again. Same thing on my unit circle. Every time I travel a full rotation, I'm going to end up with a coterminal angle, and that will happen with both of my solutions. So I go ahead and take these base solutions, and I form the general solution. So pi 6 plus multiples of 2 pi k. And then from the other one, my second base solution, 5 pi 6 plus multiples of the period, 2 pi k. K is just an integer, so it's going to be like negative 1, 0, 1, 2, ... So I'm adding or subtracting intervals of that period. Let's do another one. So here's another familiar trig value, radical 2 over 2. I know this is a 45, 45, 90 triangle. My cosine, so that horizontal leg, is radical 2 over 2. So that angle has got to be pi 4ths. Well, radical 2 over 2 as a height is about here, but it shows up twice in a period of 2 pi. So how many solutions per period? 2. Again, I have two base solutions. How many total? Well, this is 2 pi period forever in the positive and negative direction. So again, infinitely many of those. I want to find the solutions in one rotation between 0 and 2 pi. Well, I know the first one is right here where cosine is positive, and that's in quadrant 1. These have positive cosines and positive sines. The other time that cosine is positive is in quadrant 4. Positive cosines, negative sines. So the other one that I want to pick up on, and I do want it between 0 and 2 pi, almost to 2 pi, that's going to be 7 pi 4ths. So my solutions in that first positive period are pi fourths, comma, 7 pi fourths. These are my base solutions. So with those base solutions, I'm going to go ahead and add multiples of 2 pi, because that's how I'm going to get from one solution to the next. And I need to do it to both of these base angles. So my general solution looks like this: pi fourths plus 2 pi k, because it's 2 pi periodic, and 7 pi fourths, my other base solution, plus 2 pi k. We could have used negative pi fourths here, we could have, but I really want to, just to keep this general and in a universal form, I want to keep that as the first positives. Okay, next, the difference between example 3 and the examples that we had above is the period. The period for this one, we take the original period of sine and I divide it by that multiplier 2. So the period is actually pi. So if I were to trace out my sine wave, I would trace out one sine wave between 0 and pi. And then I would repeat that sine wave between 0 and 2 pi, and so on in both directions. How many solutions then on 0 to 2 pi? Well, I have two periods covered there. There's one period and there is the second period. So as I'm looking for these heights of radical 3 over 2, it's going to happen twice per period. So there's 1, 2, 3, 4. So I'm going to have double the number of solutions. So when we change the period, we really want to be careful that we're also finding all solutions if we're looking for all solutions within one rotation of the unit circle. Okay, let's go ahead and tackle some examples. Some of these we'll be able to do with the unit circle. Some will be a little more dependent on our inverse functions. Whenever we've got a common angle, though, it's easier if you can use that great base knowledge that you have of the common angle values. For this first one, for example, so I've got the sine of theta is equal to 0. Well, sine is equal to 0 over here and over here on the unit circle. This is the point 1 comma 0. This is the point negative 1 comma 0. So it's going to happen at 0 and it's going to happen at pi. I just want to find the solutions between 0 and 2 pi. This is 2 pi periodic. I'm looking for two base solutions and I found them, 0 comma pi. I could do my general solution, I'll do this like in yellow here, just to kind of emphasize what we did up above. 0 plus 2 pi k, pi plus 2 pi k. The nice thing about this example is those solutions actually happen just every pi. So we could even boil this guy down to multiples of pi. But the solution that we're looking for in that one is the 0 comma pi. I just gave you a little bonus. Okay, part B, example B. So for example B, the first thing I need to do is to isolate my cosine. I'm going to divide both sides by 2, and then I can go ahead and work with my common angle, radical 2 over 2. On our unit circle, our cosine is negative. Negative cosine happens in quadrant 2 and in quadrant 3. This is a 45-degree angle, or pi fourths. So I'm going to land here and here. So that would be at 3 pi fourths in quadrant 2 and 5 pi fourths in quadrant 3. So 3 pi fourths and 5 pi fourths. And if you're wondering when we're going to use inverse functions, here it is. I do not have a common angle for 0.7. So I'm stuck using sine inverse. As we're using sine inverse, it's a well-defined function. It's only going to give me an angle between negative pi halves to pi halves, negative y to y. But I'm looking for two base angles. Sine inverse is only going to give me one of them. So I'm going to work for it. I'll use my green. So I want to apply sine inverse to both sides. Sine of x is equal to sine inverse of 0.7 So x is equal to, I'm not going to leave the sine inverse. Let's go ahead and just get some decimals going here. So sine inverse of 0.7. Oh, you should make sure you're in radians first. I did not do that. And I am in radians. Good. Okay, so I can go back so I can quit. So sine inverse of 0.7 is 0.775. So x is approximately 0.775. Pi is 3.14. 0.775, this is 1.57. It's going to be over here somewhere, 0.775. The nice thing about the sine and sine inverse is that the other one's going to be supplementary. So if we call this number 1, the second base solution that we're going to find, x is going to be pi minus 0.775. And I can just do that right in my calculator. Pi minus 0.775. And we get 2.367. So 2.367. So 0.775 and 2.367. If you're wondering how can I check these, you can check them with your calculator. So a great way to do this is just go back into, take the sine of 0.775, and you're hoping to get 0.7 back. And we get 0.699, right? We rounded, so we're good with that. The sine of 2.367, which I hopefully rounded correctly. And again, I'm really, really close to 0.699, so you can check your solutions. But I did find my 2 base solutions. Here's another one that's not a common angle. So normally I would go ahead and apply a cosine inverse, but I noticed something, and I noticed that this is not in the range of cosine inverse. So I cannot cosine inverse, I cannot do this like I was planning on. Or I should say it's not in the domain of cosine inverse, not in the range of cosine. You could try. And if you tried, I'll bet you get a domain error. So I'm going to go second, cosine inverse, 1.2. I'm putting in a trig ratio. Trig ratios are bound by 1 and -1. Enter, and sure enough, I get a domain. So actually, that's really nice. It's just not possible. So no solution here. Looks like it might be the case for E as well. However, in E, I've got that 6 out in front. I need to isolate my sine function first before I do anything else. So if I divide by 6 on both of these, I get the sine of x is equal to -2.4 divided by 6. So the sine of x is equal to -0.4. So we are okay. Sine and cosine are bound by -1 and 1. So we're okay. We can go ahead and do a sine inverse. So I'm going to do sine inverse of -0.4 is equal to x. Let me erase this kind of in my way. So that's going to give me one of my solutions. I can just hit enter here. And then I want second sine inverse of -0.4. Make sure you use the little negative. And we get -0.412 if I round. So negative, so x is about -0.412. Did I get that right? -0.412. To find the second one, so this is 1. We need 2 base solutions. I'm going to go ahead and do pi minus -0.412. So I'm going to do pi minus negatives. Let's just do pi plus. So I'm going to do pi plus 0.412. And I get 3.554 if we round. 3.554. Now, I did find two solutions. However, they were supposed to be on 0 to 2 pi. This one is, we're good. This one is not, it's negative. But I know I can get to another solution by adding a multiple of pi. I'm sorry, 2 pi. So here is my function. We were looking for a negative 0.4, but I need the negative 0.4 on my interval. So I need to add a 2 pi plus 2 pi. So I'm just going to go ahead and adjust that one. And calculator, so I'm going to go 2 pi. Calculator, come back. So let me do this again. So negative 0.412 plus 2 pi. And that's just going to find me the next solution based on the base solution. And that one is within my interval. 2 pi is, what is it, 6.28 or something. So 5.871 is going to be my second solution. So that gets me to 5 point, a very short memory, 871. Whoops. 871. Now I've got my two solutions on the interval that I was asked for. So 0.554 and then 5.871. And remember, you can always check these. You can go ahead in your calculator and go 6 sine of 3.554. And you should get really close to negative 0.24. Perfect. And then I can do 6 sine and do 5.871, negative 2.4. Perfect. I'm feeling great about those solutions. In the next video, we'll do the examples for part 2.